how do you determine which qubit technology is the most apt for the quantum computer that you are building? Because there are quite a few variants in them as well. So how does one determine?
Well, it basically depends upon the your need. I would say, like if you're working on an optimization problem, I would say right now the D waves quantum annealers are way too good for optimization things. And well, then maybe you could have for faster operations, you could rely on something called as a superconducting qubits. And if you want a high retention of an information, the trapped ions have a very high fidelity rate. But there are even other technologies like the nuclear magnetic resonance ones are there, the NV centers. I have not completely dealt with this kind of technologies, but I have heard that they are very good. And exactly selecting a quantum platform is still an question to answer by many in this world. And if no one, I'm not sure if anyone really knows. And like there could be very mixed of opinions on this. I myself am not, uh, I would say I'm not the right person you should ask which quantum technology is where to use when. I mostly work on this algorithms point of views. But yeah, it's still in a part of research of which kind of a quantum technology is going to be the at par. But right now, as I said, like D-wave annealers, then Rydberg atoms, these all are performing, and they have their own trade-offs. And so based on your requirements, and can you handle those trade-offs or not, is what the whole thing is working around. So yeah, I don't know if I'm completely answering that question, but this is what I know.
Um, to sort of end this theoretical segment of everything, what goes into building a qubit technology? Like you did sort of were able to explain why certain qubit technologies are chosen over others, but like how is how is a single qubit technology built for that matter in the first place?
Okay. It's yeah. You are mean to say is like how are we realizing a qubit?
Yeah, how are they physically realized? Like how do we know what to do with them, and how to sort of, yeah, how to physically manifest them, like with topological quantum computing, for example, the qubit technology. A little while back we didn't know how to realize majorana fermions, and suddenly we were able to get them to work, and we realized how good they were at doing what they were. So like how
Yeah.
do we do that? Is it just a trial and error thing, or are there typical approaches to doing that? Like what is it?
Uh, yeah. It's not completely trial and error thing. It's like it's an calculated trial and error thing, kind of a stuff. But so I think I will can just answer the question on how can we realize a qubit just on for the transmons, because I have a bit understanding over it. So I'm not sure if the audience would be knowing of LRC circuits, an inductor, resistor, and a capacitor circuits. So these qubits are nothing but, as I said, are the oscillating particles with the different energy levels. So what these transmons or the superconducting qubits try to do is they have this LRC circuit so that they could replicate an oscillating behavior. If anyone has ever worked with LRC circuits during, I don't know, it's for the Indian audience who have given JEE are very much known to the LRC circuits and different equations, and how can we have an LC oscillations, a damped oscillations kind of a thing. So usually this is the basic concept. They try to just build an LRC circuits, and LRC circuits is something behaves like a qubit because of its oscillating behavior. But the catch comes is that if we see an LC oscillation equation, it's an harmonic oscillation equation. And when we try to do that, we have a discrete energy levels with similar energy gaps. Just so to avoid this thing, people use something known as Josephson junctions. The Josephson junction gives a non-linearity in the magnetic field, and which helps us in realizing an atom like a behavior of different energy levels. But since we are working with qubits, that is two energy level system, we are only concerned with the first excitation energy and the ground state. So that's how maybe a qubit is realized. It's just an LC oscillations. But again, the inductor here is a Josephson junction, which is actually playing the vital role here. I don't know if this kind of help answers the whole thing or.
I just have one query. I did understand what you were trying to explain, but just probably taking it a bit further. After realizing these qubits, how are we able to use quantum programming, or like how are we able to use programming to sort of control them? How is quantum programming different from normal classical programming? In what way? Like what goes into being able to control these qubits?
Okay, so again, we are controlling this qubit, as I said before, using microwave pulses. So when we write this pulse, okay, yeah, I think I missed this part. So let's say when you are writing gates in your in your Python program, this goes down and converts into a CASM program. This CASM program just puts it, let's say, on a controlling unit. What this exactly controlling unit does is tries to realize these gates on the microwave pulses. So we have qubits. It's an atom which is interacting. But now, how are we going to put these gate operations? These gate operations are realized as the microwave pulses of frequency of the microwave pulses which we are putting in. That acts like our Hamiltonian. So when there is let's say a, a microwave pulse oscillating in like maybe with an oscillation of pi or something, uh, we could have a certain kind of a quantum gate in that. So that operation is put on a qubit. So let's say our whole LC circuit is in a ground state, and when we put this microwave pulse, it maybe it tries to goes towards and excite. It acts like an X gate. It goes from 0 to 1. So in this, we are trying to put on the quantum operations in picture. So that's how when we write gates in Python program, this Python programs get converted into this microwave pulses. So there is this aspect, if anyone wants to read, by Qiskit pulse, if anyone has heard of or you don't know. So this is how you can actually control a quantum hardware.
And that is why, like, as we try to scale it and bring about more and more qubits, it becomes tougher and tougher to sort of have them collaborate and synthesize with each other.
Hmm.
Right. Okay, right. It's really interesting, like when you start wrapping your head around the basics and everything. But right.